Hello, good evening. Yeah, I think we are 5 minutes past the hour, so we can get started. So, welcome to week 11 of the CS100 Operating Systems course. I'm Prashanti. I'll be handling today's live session. Hope you can hear me and see my screen clearly. So, yeah, let's start with a quick recap of topics that were covered in the week 11 set of lectures. So, we were already talking about demand paging, and we looked at how do we calculate the effective access time for demand paging in the presence of page faults when the page fault rate is a particular number. We also looked at some optimizations that can be done for demand paging. Then we spoke about page replacement, and we also looked at a few algorithms for page replacement. We looked at FIFO, we looked at LRU, we looked at an optimal replacement policy, which is kind of like the ideal situation. And then in some of these algorithms, we also noticed something contrary to our expectations, and that was called Bilady's anomaly. And then we moved on to frame allocation, and we spoke about global versus local frame replacement. And we also discussed things like thrashing, how do you avoid it, and we also looked at locality and working set. So all of today's questions will be based on these topics. Let's get started. So this is an effective access time calculation question. So provided that memory access time is 300 nanoseconds, average page fault service time is 12 milliseconds, and page fault rate is 0.0001, find out the factor by which the access time is slowed down. There are 4 options. Since this is a numerical, I'll wait for a good minute so that you get time to calculate it. Let me know once you have an answer. Any answer so far? Sure, you can take your time. For people who have just joined, we are solving this question, so I'm waiting. Since it's a numerical, I'm waiting for a minute. You can also try and solve this, and when you get an answer, please put it on chat. Any answer so far? Okay. Do you need more time or should we discuss the answer? Okay, let's look at the answer then. So the answer is the slowdown is 5. So first let's take a look at how do we calculate effective access time, right? So this is from your previous lecture. So one second. Yeah. So so you have two cases basically, one where there is a page fault and one where there is no page fault. And how do you figure out which one happens? It is using this page fault rate, which is between 0 and 1. So if it is 0, it means that there are no faults. If it is 1, it means that every reference is a fault. Ideally, this value will be somewhere between 0 and 1, and it should be really small. Like if you see in this question, the rate is 0.0001, right? So if not, then the overhead is a lot, because you will see in the question itself that memory access is 300 nanoseconds. It's a nanoseconds. Page fault service time is 12 milliseconds. So this is 6 orders or maybe 5 orders of magnitude in time, right? The difference. And this is because while this is a main memory access, this one involves a swap in and swap out, both of which are disk IO, and the order of magnitude in the speeds is really high, and that affects things. So typically you will see page fault rates like this, very low realistically. And so now coming to the formula, so imagine it as two branches, right? So P times for a if the page fault rate is p, there will be this many times where there is a page fault, and there will be 1 minus p times where there is no page fault. So in the no page fault case, it is straightforward. You directly access memory. In the page fault case, you have the page fault overhead, which is basically something like a trap to the operating system, and then you will have something like a interrupt service routine which actually services this page fault, and as part of that you will also swap a page out and bring a page in, right, both of which are disk IO. So this entire thing will have to be multiplied by the p that is given to you, by the rate of page fault. So here again you have the page fault service time. So we will assume this page fault service time to capture all of these things, the overhead, the swap time, etc. So the rate is given to you. So 1 minus p times there is no page fault, and that time it would straight out be a memory access which takes 300 nanoseconds. The other time, which is p, it would take 12. Okay, this should be milliseconds. It's a typo. Let me fix it right away. I didn't notice that before. And I think below it is converted to nanoseconds. So yeah, below it is probably right, but basically if you use this formula and calculate, then you get 1500 nanoseconds. So this is somewhat like an average access time, right? Whether there is a page fault or not, what would an average access time be like? And that comes out to be 1500 nanoseconds. So the slowdown is this 1500 divided by 300, which was the original memory access time, and that is a factor of 5. So your answer here is 5. So the question is not asking what is the effective access time, it's asking what is the slowdown. So we do this final part of the calculation. Any doubts in this? Right. Yeah, these involve a lot of calculation and a lot of manipulation with units, right? Like you saw here, this was milliseconds, this was nanoseconds. So if you miss out some of those things, then you end up getting a very different answer. Okay, if there are no doubts, let's move on. Frame allocation algorithm determines how many frames to give each process, which frames to replace, both A and B, none of the above. Okay, A, how many frames to give each process? Anyone else? Okay, if not, let's look at the answer. So the answer actually says both A and B. So this is again a previous year NPTEL question. So, and it looks like your slides also have this exact statement saying the frame allocation algorithm determines both how many frames to give to each process and which frames to replace. But if you ask me, right, this is a bit of an ambiguous question, and if you said A is the answer, I think that is still fine because that makes sense, right? If you're talking about frame allocation, that does not necessarily include replacement. So A as an answer would be acceptable, but the official NPTEL answer key for this question is C, which includes replacement. One way to justify that answer would be to think of what happens during a frame allocation, right? So you are trying to give a certain number of frames to a process, but in case you do not have a free frame available, you might need to do some frame replacement. So you can argue that that replacement is done as a part of the frame allocation itself, and therefore both of these are deemed to be functions of the frame allocation algorithm. That's one reason I think the answer might have been given as C. Since this is an official NPTEL question, I'm not changing the answer to A, but in my opinion, A is a valid answer too. I see. I don't know. I've noticed that with my camera last week as well, but I have no idea how to fix it because my network seems to be okay. So I changed cameras recently. I'll try and figure it out before the next class. Any doubts on this question? Is there a problem in hearing me and are you able to hear me clearly and see my... Okay, the screen sharing is also lagging. I see. Let me try switching to a different network and let's see if that helps. So the call might get disconnected. In that case, please rejoin. I'll just switch networks. Is this any better? Can you see my screen change? Okay, great. Thanks for letting me know. Great. So is question 2 clear? Is the answer clear to this? Okay, if yes, let's move forward. Can we also give the argument regarding frame allocation algorithms? Which are the one I just said about how allocation could include replacement? That would mean that the answer is A and B. If you wanted to argue that the answer was A, then you can say that allocation is just about giving frames to every process. But since your slides has this exactly, I don't think I can change the answer key here. It's kind of an ambiguous question. That's what I would say. Great. Let's move on. Page replacement algorithm wants the first axis to have the lowest page fault, wants re-axis to have the highest page fault, change the reference page numbers, none of the above. Any answers to this? Okay, D, none of the above. That's okay if you're not sure. Any other answers? Let's take a look at the answer. So it is wants the first access to have the lowest page fault. So going back to your slides on page replacement algorithm for this week. So ideally we want a page replacement algorithm that gives you the lowest page fault rate throughout, whether a process tries to access something for the first time or whether it is a re-access, it wants the page fault rate to be the lowest. Now how would you kind of get the intuition behind this? So if you had an algorithm like the optimal one where you're able to predict the future accesses, you can bring in those pages before even the accesses are made. So in that scenario, your first access would also not have a lowest page fault, would also not have a page fault. Similarly, an algorithm that is able to predict the future based on the past or something else would ensure that the page is kept in if there is going to be a re-access. So an ideal page replacement algorithm is one that gives the lowest page fault rate on both a first access and a re-access. So here the options are: the re-access has a highest page fault. No, we do not want that. We want the first access to have the lowest page fault. That is true. Change the reference page numbers, not really sure what that's about. So since A is the best option we have here, we go with that. Is this clear? Any doubts on this? Okay, let me read that. Lowest page fault, when we start with no pages in the frame, we would be encountering a page fault. Ideally, yes. There are strategies that do things like prefetching, right? Before even you start, you might want to fill up your memory with certain pages that you think will be accessed, because again, as we saw in the previous question, if there is a page fault, the access time becomes very, very different. So we want to avoid them as far as possible. So even for the very first access, you might be able to avoid a page fault. And I'm not saying there are algorithms that do that very well, but if we are coming up with an ideal algorithm, that's what we would want it to be. Okay, so yeah, I think there's nothing else here that you need to look at. So yeah, this is how we evaluate them, just the way we used for, if you remember when we had processes and scheduling algorithms, we used to use this example of different processes having different burst times and arrival times and evaluate our scheduling algorithms using those. So similarly here you have a string of page numbers and we take memory to have a certain number of frames, and we try and see how often there are page faults and how often there are no page faults, and this will help us evaluate how good that particular page replacement algorithm is, which we'll see in a few other questions. So moving on, what is Bilady's anomaly? When we use FIFO for page replacement and more pages does not affect the page fault count. When we use FIFO and more pages reduces the page fault count. When we use FIFO and more frames leads to more page faults. None of the above. C, when we use FIFO for page replacement and more frames lead to more page faults. Okay, anyone else? Also, since we are almost midway in the session, if you have any doubts in this week's lecture or maybe the previous week's lectures, please post it on chat. I'll try to take it towards the end of the session, or if that's not possible, I will answer them in the next session that we have. But don't hesitate to, yeah, sure, you can ask it anytime during the session. Since people join and leave, I ask at 2-3 places so that if people have doubts, they can post it as soon as they can. But you can ask it towards the end, no worries. Okay, let's look at the answer. It is C. When we use FIFO and more frames lead to more page faults. So this is again a recap. So the intuition that we have is that we have a certain number of frames, and if we increase the number of frames that are allocated to a process, correspondingly the page faults would decrease, right? Because you are giving a process more memory now. So the intuition goes that okay, a few more of the accesses that it makes will not lead to page faults because of these extra frames that are there, and they would have those necessary pages. But remember this, we took this reference string and we tried doing this for 3 frames and 4 frames, and we found something counterintuitive, right? And that's why it's called an anomaly. And what is counterintuitive there is, even if we increase the number of frames, we might not actually decrease the page faults. It might lead to more page faults, and you can see that in the graph here when we go from 3 to 4, right? The number of page frames increases, but the number of faults also increases. So this is somewhat of an unexpected behavior, and it's called an anomaly. So that this question just asks about what is it. So this is the explanation for what it is. But I want you to think about this, right? So I think, okay, I will ask this question after a couple more questions, because I think there's one more question on the lady's anomaly. Let's wait for that. Any doubts on this question itself? Okay, if not, moving forward. Among the following algorithms, which one has the least rate of page fault? FIFO, optimal, least recently used. Each one has similar page fault outcomes. B, optimal. Okay, anyone else? Anyone? What do you think is the answer to this? Okay, let's look at the answer. It is optimal, as the name says. So optimal is, again, if you remember in scheduling, we had this things like what was that, shortest job first, right? And there were algorithms that tried to that used the assumption that the burst time would be known, which is an unrealistic assumption. You wouldn't know that for a process. Similarly, but why do we have that? It acts as a benchmark, it acts as a reference. So this is the best you can do, and how does something else compare to this? And that's a way you evaluate it. So even if it's theoretically not possible, it serves that purpose of being a benchmark. So similarly here we have this optimal algorithm. So it presumes knowledge of the future. So it knows which page is not going to be used for the longest period of time. In essence, it has access to this reference string, or it knows what memory accesses are going to come. So that's how, and it uses this assumption to make its replacement decisions. But the reality is that you can't really know this, right? Unless, so as an OS especially, you can't know this. Maybe you're coming up with an application, and in that case you will know, you might know what the access patterns of the application are, and in that case you might be able to come up with a very good page replacement policy that caters to your application. But as an operating system, where you have, as a general purpose operating system, where you have a bunch of applications, each of which has different access patterns, it is quite impossible to figure this out, right? So this is again used as a benchmark to see how well a given replacement algorithm performs. But coming to this question, optimal is the standard one which has the lowest page fault. You can't get any better than that. Any other algorithm will perform worse than this in terms of page faults. Any doubts here? If not, we will move to the next question. Which of the following algorithms does not suffer from Bilides anomaly? FIFO, optimal, LRU, both B and C. Anyone? Okay, D, both B and C. Anyone else? Okay, let's look at the answer. It is both B and C. But let's get a quick recap of FIFO and LRU. So FIFO is, as the name indicates, it stands for first in, first out. So if you have to look for a replacement page, what you do is you replace whatever came into memory first. So you have an example here. We won't go through the whole thing. We'll go through maybe 1 or 2 steps, right? So the assumption is that we have 3 frames here, and the reference string starts like this: 701. Initially everything's empty, so you start with 7, then you bring in 0, then you bring in 1. Now you have an access of for 2 which is not present in these frames, so you need to replace one of them. Which one do you pick? You pick 7 because it came in earliest, so first in would be first out, so you replace 7 with 2, right? And next you try to access 0. There's no page fault because 0 is already there. Then you try to access 3, which again is a page fault, and you need to replace a page. So now you pick 0 because that's the oldest one in this existing list. So the list becomes 2, 3, 1 and so on. So you can count the total number of page faults for this reference string, and that comes out to 15. This is FIFO, and it's one of the simplest ones that we start with. Next we take LRU, and LRU uses knowledge of the past. So we saw optimal earlier where it presumed that it knows the future, right? So it's an unrealistic assumption. LRU uses a more realistic assumption that it knows what has happened in the past, and based on this it will replace something that has not been used for the longest period of time. Interestingly, LRU is the default that Linux uses, and I think many other operating systems also use LRU, and this may or may not be a very friendly policy depending on the access pattern of each application, but this is what is typically used. So what it does is it replaces a page that hasn't been used for the longest period of time, and as you guys saw, there are different ways of implementing LRU. The policy here is just that you should replace something that hasn't been used for the longest period of time. So we won't look at how to implement it here, but that's anyway there in your lectures. So again we take the same reference string, so we bring in 701, right? And now when 2 comes in, we replace whatever was least recently used, which again happens to be 7, and 0 is asked for, and 0 is already present, so that's not a fault. And then 3 is asked, 3 is brought in. Here's the key difference, right? FIFO would have replaced 0 because 0 is the one that came in first, but LRU replaces 1 because 1 was the one that was least recently used. 0 was just now accessed, right? So 1 is replaced here. I won't go through the rest of it. I think it is clear till here. And now your text says that LRU and optimal are cases of stack algorithms, and they don't suffer from Bilides anomaly. So the answer is LRU and optimal, and therefore both B and C. But this is an interesting thing, right? It makes you wonder why certain algorithms suffer from Billy's anomaly, why certain other things don't, and what does this mean, right? So I will leave this as an open question today, and maybe address it in the next class. But does anyone have an answer to this? Why these don't suffer from Billy's whereas FIFO suffers from Billy's anomaly? Yeah, why is it that stack based algorithms cannot suffer from Billy's anomaly? Think about it. That's okay. That's not part of your regular NPTEL questions. It's just something you're curious about. Okay, because we can show that the number of pages in n frames will be present in the number of pages in n+1 frames. Right, that makes sense. I think this was also there in the Galvin book. So maybe you've already read that. For anyone who has no idea about this, think about it. And if you're still not clear on why this is, ask me in the next class. Otherwise, I'm going to assume that you know and leave it at that. Nice. Okay, moving on. Which of the following counting algorithms are expensive to use and considers the argument that the page with the smallest count was just brought in and is yet to be used? LFU, MFU, both A and B, none of the above. So we have one answer that says MFU. Anyone else? No one else? Okay, let's look at the answer. It is MFU. As a quick recap, so you could do all of these things, right? They're different ideas and there is no one right answer here. So least frequently used replaces the page with the smallest count, and the count here represents the number of references that are made to each page. So if a page has the smallest count, one way you can interpret that is that it is least frequently used, and therefore you say this is not being used much, so I'll replace this. Another way to interpret it is what MFU does. So if you see a page with the smallest count, then you assume that it was just brought in and it's probably not used, which is a valid stance to take, right? You might have just brought that in and therefore it has a very small count. So instead what you do, you replace the page with the largest, you replace accordingly, right? And so coming to this question, which of the following are expensive to use? Both are expensive to use, basically because you need to keep this counter of number of references. And which of them considers the argument that the page with the smallest count was just brought in and is yet to be used? So that is MFU, right? So that's why the answer is MFU for this. Is this clear? Okay. Let's move to the next question then. Which of the following statements is true? The process execution time can vary a lot in local replacement than global replacement. The memory utilization is better in local replacement as compared to global replacement. A process selects a replacement frame from a set of all frames in global replacement, while each process selects from only its own set of allocated frames in local replacement. all of the above. Read these carefully. I think each of these are quite long, so okay. C, process selects a replacement frame from a set of all frames, while each process selects from only its own set of allocated frames. Anyone else? Okay, the answer is C. So let's take a look at both global and local replacement, right? So how do you, again, this is a choice that you could make. And what's the difference between them? Global replacement is when a process can select a replacement frame from the set of all frames, not necessarily its own. It can take a frame from another process. So what is the consequence of this, right? A process's execution time can vary greatly because this would depend on how many processes are in the system and how they behave, right? For instance, you might have something that, if you had a process that was malicious, it might intentionally try and replace frames from a certain other process, although there are a lot of checks and guards for such things. But basically there is a bit of non-determinism here, because you're giving a process sort of the ability or the capacity to pick a replacement from any other process frame, right? Therefore the execution time varies a lot, and a single process cannot control its own page fault rate because some other process might come and take away its page and things like that. Whereas with local replacement, every process can only select from its own set of allocated frames. So the non-determinism comes down and you get a more consistent per process performance. And if a process does not have a sufficient number of frames allocated to it, then it will suffer from many page faults because it can only replace its own pages. And if we assume that there are not sufficient frames allocated to it, then it would keep on replacing and it would still hit page faults, right? Because this number that's allocated to it is too small, so it would result in thrashing and underutilized memory. So let's say the opposite happens, a process gets allocated a large number of frames and it's not really using them, but no other process is now going to come and take away these frames, so they will sit in memory although they are not very well used. So those are some of the disadvantages of local replacement. So now coming to this question, it says execution time can vary a lot in local replacement, which is not true. The opposite is true. Memory utilization is better in local replacement, again not true. It's actually poorer in local replacement. So the third option is the right one, which says that it can select a replacement frame from the set of all frames in global replacement, while in local replacement it can only select from its own set. So this is the only correct option here. So all of the above will not work and C is the right answer. Any doubts on this? If not, let's move to the next question. Which of the following statement is true about thrashing? It makes the operating system thinks that it needs to increase the degree of multiprogramming, leads to low CPU utilization, a process is added to the system, all of the above. Okay, all of the above. Anyone else? it is all of the above. So let's look at what thrashing is. So as we said previously, right, if a process does not have enough pages, then the page fault rate is very high, because you have a page fault to get a page and then you go through this whole replacement. But after you replace it, maybe within 2 or 3 accesses, you need this replaced frame. So you'll again go through this. So it's like mindlessly going through more faults and replacements, simply because the amount of memory that you have allocated, the number of pages that you have allocated is not enough. So what happens as a consequence? There is a low CPU utilization, because there is a lot of this context switching to the OS for the page fault handling. Then there is disk IO, and then the scheduler comes in and maybe brings in another process to run, and so on, right? So as a result of all these overheads, there is very low CPU utilization, and the OS, which monitors this CPU utilization, thinks that maybe the CPU is not being utilized fully by this process alone. So it might bring in the long-term scheduler, increase the degree of multi-programming, or add another process to the system. So thrashing is basically when a process is busy swapping pages in and out without making much progress, because every few accesses it leads to a page fault, and this is what keeps happening. So consequences of thrashing are all of these. So low CPU utilization, yes, makes the OS thinks it needs to increase degree of multi-programming, yes. Process is added to the system, also yes. So the answer to this is all of the above. Any doubts on this? Okay, if not, let's move to I think the last question we have for today. Which of the following does not help in limiting the effects of thrashing? Local page replacement, global page replacement, priority page replacement, none of the above. Answers to this? Okay, A, local page replacement. Anyone else? Okay, let's take a look at the answer. It is global. Okay, which of the following does not help? Okay, it is global page replacement. Let's look at why that is. So as we saw what was thrashing, right? And now how do we limit thrashing? One of the ways to do it is local page replacement. So because you're now constraining the replacement to one single process, other processes might not suffer from thrashing. Another way to do it is use some notion of a priority. So you might say that I will replace pages only from a process with the lowest priority. So in a way, it's containing the effects of thrashing. It will not eliminate thrashing, because this one process, either with the lowest priority or the process itself which is trying to find a free page, will still suffer, might still suffer from thrashing, but you're limiting thrashing because you don't have this problem like we did in global page replacement, where multiple processes could suffer from thrashing. So that's why they are both A and C help in limiting, B does not help in limiting. Any questions on this? Okay, if there are no questions, I think I had a couple more slides. Okay, your reasoning was that number of pages allocated to a process is lesser than the minimum number of pages it requires to execute. Yes, that's when there would be thrashing. Frame allocation algorithm will make sure to allocate minimum pages at least. Okay, great. Okay, got it. Makes sense. So I think I had asked this last time, so I just put in an answer. So how does the OS or the kernel figure out which is the active page table, right? Every process has a page table. So I think I got an answer then itself that it is PTBR or the page table base register, which is correct. This is popularly known as the CR3 register on x86 systems, and it may be called by different names, right? When you have a flat page table, it might be page table base register. When you have a hierarchical page table, as you do on most x86 systems, it might be called PDBR, which is page directory base register. So there's this notion of a directory and then a page and so on. So there are 3 to 4 levels in the hierarchy. And whenever there is a context switch, the PCB will have this value of the PTBR or the CR3 register, and that will be populated to the actual hardware register. So whenever the OS needs the current running processes page table, it will simply go look at the PTBR. Hope this is clear. Okay, I have a couple of questions for today also. Think about this, because there's one level of thinking that happens when I give you 30 seconds and ask for an answer, but some more questions might need a lot more thought, right? So I prefer to leave a couple of open questions in every session and then maybe get back to them later. So what happens to the TLB during a context switch is the first question I want you to think about. So, and then after you think about that, what happens in a multiprocessor context? Would there need to be something done differently? So for instance, in paging, right, we said upon a context switch, the PTBR is populated with the correct value from the PCB of that process. So what needs to be done for a TLB this way? This is one thing I want you to think about. Then the second one I already asked, so I'll just skip this. Think about these two. If you want me to answer them, let me know. I'll put in a slide in the next session, which happens to be our last session. And now I think we can take any questions on this lecture or previous lecture or anything like that. Okay, sure. What do you think happens in a uniprocessor architecture? I see, it was taught. Okay, might have forgotten it. Okay, maintain a process ID. Right, you could kind of do a selective invalidation. instead of doing a full flush. Okay, so you already have the answer to that part. That's great. Think about the multiprocessor thing. I think it needs a little more thought. Good that it was not covered in your course, so think about it. And are there any other questions on the lectures? Please feel free to ask them. Okay. Pages can be shared during process creation with the fork system call, thus speeding up process creation. So you want to understand this better? Is that the doubt? Okay, okay. Right, I think long ago, right, when we were talking about processes and fork, I had this slide in my deck. I don't know which week that was, but I had a slide on copy on write, right, where we talk about when a process is forked out from the parent process, initially both of them share the same pages. As in, maybe I'll draw this out, and I have that diagram also there. You can maybe go look at it. So if these are the pages given to P1, right, and you fork out P2 from P1, ideally what the operating system should do is copy out this entire address space for P2 also, so that P2 has a copy, but physically they are not the same. So P2 can edit its own copy and P1 can edit its copy. But as an optimization, what the operating system does is it shares the same pages between the processes, as in there's only one copy and both P1 and P2 are pointing to it, right, in a sense. And this works as long as P2 does not make any edits to any of the pages. The moment it tries to edit anything here, then the OS is forced to make this copy. So then it will go ahead and make this copy and give P2 an access to that, so that P2 can continue its editing here. So what you get as a benefit of this is that when I execute fork, because I'm not actually doing this copy, I get a very fast response, or the process creation is speeded up, as your slides say. So this optimization is called copy on write. You copy the pages only when there is a write. So it's a lazy way of dealing with things, but it is performant. So that's the trade-off. So whereas the advantage to that is if P2 never makes a change to this address space, maybe it calls some other process entirely, then you wouldn't have wasted time initially copying all this over, because anyway now you have to replace the address space by something else, right? So that's why this optimization is beneficial. In most cases you expect this process to do something else. It's not going to be using the same stuff and editing something here. But if it does, then you have to pay that penalty. The first time there is an edit, you will see this entire cost of copying the pages. So that's the optimization that's popularly known as copy on write. There is a slide in my old decks, maybe week 3 or 4, I think. If you can go look it up, I think you'll understand. But hope this is clear. Yeah, I think that's the point of having live sessions, right? Sometimes we read things a lot and then we don't, because sentences in textbooks and therefore courses are written in a very condensed fashion. And for the people writing it, right, most often they have been studying the same subject for 20-30 years and they're teachers of that subject. So they don't need to explain it in a lot of detail. So they try to write it as condensed a manner as possible. But when you're trying to understand it for the first time, it may or may not be obvious and it might end up being more confusing as to what they're referring to. So because we have these live sessions, there is an opportunity for that interaction and clearing things out quickly. So feel free to bring questions even outside your lectures. Like you said, if you find something in Galvin that you don't understand, feel free to bring it up. Unfortunately, we have only one more session next week, so bring whatever questions you have to that one, and we'll try and spend more time maybe on answering the questions there. So I think we are okay regarding process states. Sure, feel free to ask. Okay, what exactly happens in new? It's easy to understand ready, running, and blocked, but not new. Um, I don't remember, to be very honest. I will look at the slides and Galvin and come back. It's probably about when a process is getting created and um, when the OS is doing some bookkeeping for it to go to the ready state. But I don't want to give you such a vague answer, so I'll try to look it up and then give you a more precise answer in the next class. Great. Any other questions? Okay, great. Thank you. So see you next week and bring whatever questions you have because it's the last session. And hope you had a good festival. Have a nice weekend. See you next week. Thank you.